everybody
Join and
to
participate.
our penultimate meeting for the academic year.
We
And,
can. I just thought I'd lurk the
An
first
especially
time.
warm welcome to anybody who's with us for the first time, or anybody who's in from the other clubs. We are really glad to see that even in the face of this pandemic, we can reach out to so many people and so many different clubs and share what we have with everybody else. So without further ado, I'm going to turn the meeting over to our esteemed program chair to, oh, wait a minute. Oh, Don's up first.
Yeah, I thought you were going to say Don.
Don's up first. Sorry about that.
Take a look at the night sky real quick.
Yep.
Okay, but first of all, we got to see what's going on with the Mars rover. So let's hope that,
Love a Marvin the Martian.
Marvin.
No, Marvin.
Okay, can you see?
Yep.
Yes.
Looking good, Don.
Okay, so let me start out in the west like I usually do. Then we spent the last couple of meetings talking about this stuff, and it's going down, so we're not going to worry about those things right now. Mars is somewhere up here. There it is. There's Mars. That's worth looking at. Mars is, what I was looking at when I was out last Tuesday was Mars, and then looking for these three very interesting clusters in Auriga, but the sky was so hazy, I could barely pick them out. But these are going to be heading down into the west soon. So if you want to take a look at a couple of nice open clusters, 36, 37, 38,
yep,
are nice to study because they're all slightly different. And this part of the Double Star Club, I think Frank has that. I'm working on it. Let me tell you, you want a challenge, look for the Double Star Mesa. It's at the, I call the Hat of Orion. I'm not sure if it's really a hat or not, but it's at the nose of Orion. This is really, the real had to go to 165 power to get this thing to pop out. So wow, this is a tough one to split, but if you want to challenge some night, take, I would recommend a good refractor and look for the Double Star Mesa in the face of the nose of Orion.
Yeah, isn't that a Mel cluster up there?
A what cluster? Yeah,
I think
it's
it's
considered
Mel
a
cluster up there.
Yeah,
I don't know what the number is, but
yeah, I'm not sure either, but that is considered a cluster. Yeah.
Can I refill your cup?
If you like.
So
Oh, there's no positive.
No.
using up here to M35, this is a beautiful open cluster. This is pretty easy to find. You just go down the feet of the twins, okay, down the twins, and you can center in and zoom into that. It's easy to see. It's fairly bright. It's a beautiful open cluster. I was looking at that. That even with a hazy sky, that shined through the haze, no problem. And of course, one of my favorites that I can never resist, especially with binoculars, is any pair of binoculars will capture this. And this would be absolutely beautiful. In fact, with the telescope, it's hard to see because it's so huge. All right, and last month, I know we talked about the Leo triplet. I won't go there again, but it is down here. Talk about Algeba a second. So the double star I showed you earlier is a really tough one to split. Algeba, you can do with any binoculars. You can see the double star right here. And historically, this is a very important double star. William Herschel observed this, and it was what helped him to understand that although they knew at the time when he was around that the planets went around the sun, they didn't really know that stars also orbited. So this helped him understand and explain that stars also orbit each other. So that's, and that is, of course, right at the neck of Leo the Lion. From there, here, if you go to get to a dark sky sometime, it's not really labeled. This is called the Coma Cluster. And the first time I went up to a dark sky site up on the Poconos, I said, what the heck is that? And it's a very faint cluster, and it's very widespread, but it will stand out, and it was something to see. It's a beautiful fuzzy spot in the sky. So globular cluster time is here. This is what where the article I wrote in the newsletter was about M3. Easy to find and absolutely gorgeous globular cluster. This section of the sky is filled with globular clusters. There's many to see. I think there's one. Here's another one. This is the snow globe cluster. M53 is also a globular cluster. So there's lots of things, lots of globs to see this time of year.
Pretty famous.
Mhm.
And galaxy-wise, we looked at the triplet last time. A really fun and easy to find pair of galaxies. If you go to the Big Dipper and take these two corner stars and just extend the line out about the same distance, you come to Bode's Nebula.
M81.
Named that because he didn't really know what it was back when it was discovered. Turns out to be actually two galaxies, 81 and 82. And these are you see because they are very different shape. This is actually called the cigar galaxy, M82. And these are not hard to find because of all the help you can get from the Big Dipper. And we'll keep going around the sky. One of my favorite objects I've talked about often, I'm going to talk about it again, is right here. This is Kemble's Cascade, okay? At the bottom of it, there's an open cluster. But Kemble's Cascade is just a long string of stars, and it is very, very interesting to see. A good binocular object, not very impressive in a telescope. And that brings it back to where we started. So that's what I'm looking at these days.
Fantastic. Thanks, Don.
Thanks, Don.
Thank you.
All right, Bruce, you're on.
Okay, so I think our speaker tonight probably doesn't need introduction to club members, but I don't know how many people outside of the club are joining. So for those of you who don't know, John Conrad is a society member, and he's also a NASA ambassador. He got his aeronautical engineering degrees from Purdue and the Air Force Academy,
Sure.
and at a very early age was involved in various aspects of the space program with the Air Force, with NASA, and then with the aerospace industry. And then when he retired, he actually became a NASA ambassador. So John has spoken to our club and many other astronomical societies and the Planetary Society on a variety of topics, all of which have been, really engaging. Tonight, he's going to sort of continue on a topic that our speaker from last month addressed, who he had spoken on the Spitzer Space Telescope. And John's going to talk about NASA's infrared platforms, the importance of infrared astronomy, and then go through the major observatories, Spitzer, Hubble, and the hopefully soon to be launched James Webb Telescope. So without further ado, John, always a pleasure to welcome you. We look forward to hearing from you tonight.
All right. So I'm going to share screen here, I think, just a second.
All right, good enough. Eddie is coming to your street or wants to.
Hi, guys. You might just want to tell everyone to go on mute while John's talking.
Yep, let's all
We have
do that. Please mute your audio.
So can I ask you, did I share my screen or do something wrong?
I'm not seeing your screen.
Yeah.
I don't see your screen.
Does somebody have to give control to me first or something? I click on the button, but
You should have control. I never restrict anyone. And try it again. There, all right, now you're good. Now we're good.
got it?
Got it.
You're good, John.
Okay.
Good.
Let me get this out of the way at the side. All right. And you can hear me all right?
Yep, very clear.
So this time, Don, I promise I won't turn my speaker off. So if there's some questions and you want to interrupt me, feel free.
Okay, great. I'll watch the chat. If you have questions, please put them in the chat, folks.
All right. So greetings to everybody again. It's always great to be here. And the juxtaposition of this talk with last month's was not in any way something that Bruce had told me about, nor is it anything that, as it turns out, didn't work out as if Bruce were a genius, because
Stop there,
John. I'd rather be lucky than smart any day, right?
John,
At any rate,
camera off.
last month you got to hear from a genuine scientist, somebody who actually understands infrared to the nth degree. And actually, I did work with infrared sensors a lot as an engineer. But at any rate, you heard it from the horse's mouth at JPL. All you get from me is the secondhand use of JPL slides and other people's slides. So there's quite a different level of science in these things. And I, with some trepidation, went to the YouTube video of last month's talk and went through it very carefully to see how it might impact my talk, which has been prepared for the last 4 or 5 months. And as it turned out, I did not actually choose to talk about Spitzer. And so it's just kind of magically complementary, I think. And hopefully he went deep in some things where I don't. And also I certainly am going to talk about platforms that he didn't. So let's get on with it. The first platform that I'm going to talk about, if I can get my slides working here, is not a space platform, but an airborne platform. And as you're aware, the first A in NASA means aeronautical, and they have quite a fleet of observational aircraft, ranging from drones to small planes to props and jets. And this is the very largest that they have, the Sophia platform, which we'll talk about today. And I am going to talk about space platforms for infrared observations, just not Spitzer. Spitzer is not, as you know, operating anymore. Hubble still is, fortunately, and Hubble has done the best that we can do with its reach into the near end of the infrared spectrum, and we'll talk about that. And then the next great space telescope in the lower right there, with everybody crossing all fingers and toes, please, will be launched on Halloween, finally. So that's really exciting, and I'll tell you about that. So I thought we'd just start off with kind of a graphic reminder of what it is about infrared that's so great. And this is one of the Space Telescope Science Institute's great videos on the 23rd anniversary of Hubble about 8 years ago. So we zoom into Orion and the left or easternmost belt star, and there's this wonderful molecular cloud that blocks in the visible and gives us this nice shadow shape of the horse head. But when you reach with Hubble out into the infrared, you get to see through that bunch of cloud as well as into the cloud in a way that infrared gives us a lot more information. And the same institute, STSCI, put out a video much more recently, just in January. And this one will help you to understand about looking deep. And so picture looking with Hubble and searching for the darkest place you can find in the sky, which is basically what they're doing here. And they keep zooming in further and further, looking for a place where there's nothing in the foreground. And finally, they found this area, which became the Hubble Ultra Deep Field. And they chose it, like I say, because there wasn't much of anything nearby, so they could look very deeply. And so we're going to talk about deep seeing today in the sense of looking not just back at great distances, but looking back in time. And this wonderful video, if you want to take a look at it, is available online, and it goes on for quite a while. Shows you that there are only a few stars in this entire image. Everything else is a galaxy, and there's a whole variety of spirals and irregulars and ellipticals and so on. So we'll go on from here. So I find it as, you know, that it's useful for people at any level of science to understand the way the electromagnetic spectrum gives us energy from the very highest frequencies or shortest waves at the right there, stretched all the way across to the very longest waves in the radio part of the spectrum on the left. And so you go from high energy gamma rays and X-rays across through the middle to the regime that's very aptly named visible, because it happens to be where our sensors, the rods and cones that Don talked about in his class, are sensitive, and therefore the human sensor sees what we call visible, and vice versa. And as you go further in stretching the wavelengths to the left there, you go into the infrared, and then through the microwave to the radio, out to waves that are as much as a kilometer in length. And if you've never heard of very, very low frequency, it's quite an experience, sort of like feeling an earthquake from a distance or a rocket rumble. It's the very low frequency literally gets kind of inside you and vibrates things. At any rate, I wanted you to see it this way so that you can understand one of the reasons why infrared is special. Not that it's better, but that it's different. And I guess, you know, you could say, well, of course, every part of the spectrum is different than every other, and that's true. But infrared, by having waves that are stretched more, means that they miss more particles when they're trying to pass through a medium. So if you take, for example, the atmosphere, a box of atmosphere with dust and water vapor, and so you pass light through it, and the shorter waves in the blue and so on get bounced around a lot because they're shorter and they can't get around the particles as easily. And that's why the sky's blue. And the longer waves through the yellows and oranges and reds, they are less scattered, and so they pass on through. And what that means, if you have a scattering medium, is that more of the things beyond red into the infrared and so on can get through that easily. And so here's an illustration of how that works for us, trying to see objects in space. At the top of this image, with the direction actually flipped from the last one, with shorter waves on the left and longer ones on the right, you see all of the energy across the spectrum coming into the top of the atmosphere. And if you have a satellite out there in space, you don't have to worry about this. But when you get down into the atmosphere, the light only gets so far, or I should say the energy. And so the part in the middle there that can get all the way down to the surface, or especially to mountaintop observatories, is not just the visible, but some parts of the ultraviolet and the infrared. And so you get good seeing, but it's limited around the visible wavelengths. And so if you can raise your elevation a bit, you can get quite a bit further out into the infrared without going too much higher. The planes fly only about maybe 2.5 times as high as some of our observatories, but they give us much better transparency to infrared, and we'll talk about that. So what are the special kinds of things that we're able to see in this part of the spectrum? One of them was in the Horsehead Nebula video there, where clearly you can see through those dust clouds, and that goes along with what I just said about longer waves miss more of the dust and the scattering. At the same time, you want to see into those clouds, and that's so that you can always see stars in the visible. They're hot and bright enough, but things that are cooler, like the regions where the interstellar medium is collapsing into clouds, and where it's actually collapsed all the way down into spinning protoplanetary systems where there's still no star. It's quite a bit cooler, but the infrared is able to see things that are cooler. So we can see those star forming regions in the clouds much more easily in the infrared. And a particular characteristic that's not advertised a lot is the fact that the spectra of life-related molecules, hydrocarbons and organic and biogenic molecules, is easier to nail in the infrared than it is in other parts of the spectrum. So it's very useful for that. So for the search for life. And not necessarily tied to the infrared part of the spectrum, but since we're going to be talking about an aircraft, I wanted to note that it's much more much easier if you can move your platform around to get the perfect geometry to look at occultations. I imagine that plenty of you folks have taken your telescopes wherever out in the driveway or the backyard or whatever, and tried to time out and look for stars that go behind disks like moons and planets. Well, if you have a platform, a plane, that's flight plan is driven by a computer, then you can very precisely nail down occultations and see things, as you'll see an example of here in a few minutes. All right, so let's get to the first platform. SOFIA, aptly named, where the I is for infrared, because from the beginning, 30 years or so ago, it was designed just for observation in that part of the spectrum. And we'll talk about the components of it and how it works. At the heart of it is a large telescope with a primary about the size of the Hubble. And it's in a Boeing 747, as I've mentioned. This is based, not surprisingly, with many of the NASA aircraft in the desert in Southern California. It used to be called NASA Dryden, and sort of in honor of the Apollo celebrations, they've renamed it NASA Armstrong in the last few years, and you can probably guess why. This facility is co-located with Edwards Air Force Base, where all the test pilots fly. And so Armstrong and all the rest of the early astronauts, who all had to be test pilots to qualify, flew out of there. And so Neil Armstrong got to put his name on that facility. The science and mission people are actually based at a different center up in the Bay Area, NASA Ames. And you may be able to read on the tail is another logo, and that's DLR, which is the German words for the German Space Agency. And they get that billing and that credit for having spent 20% of the money all the way from the beginning through the development and the operations of this platform. So they're a big partner to NASA. The first flight, just over 10 years ago, and it took a few years to get to what's called FOC, full operational capability. That took place in 2014. And once they got to that, they started a rhythm that's really, I think, quite remarkable. They only fly at night, not surprisingly. They have all-night flights, again, computer controlled. The flight controls are just taken over, and it flies curving flight paths in order to maintain the azimuth that they want to, looking out the side of the aircraft. And they fly an average of 1 every 3 days, year-round, and have for half a dozen years, and now have another 2/3 of their lifetime to go, if all goes well. They don't just fly out of the California desert to look at the northern night sky. They get to go for a month or two down to New Zealand every year. And they go to the same airbase that's used to outfit and supply all the Antarctica bases. And so they go down there in the winter time when those bases aren't up and running, so they can use the flight facilities there.
John?
So 3 big parts to the SOFIA system. The aircraft, interestingly, is one that was not, did not have its first purpose for NASA. It was repurposed for NASA in the 90s after having about a 20-year career with United Airlines, for whom it was built. And it flies at about the same altitude as it did then after the modifications. And I don't know about the rest of you, but I had a chance, especially in the 70s and 80s, to fly 747s a lot, and it's without any question my favorite ride. So I'm a little envious of these guys just simply for that. So the second big part is the big important one to us amateur astronomers. And next time you grumble about lugging, your big telescope out to the pickup truck or your car or out to the backyard. Think about having a 37,000-pound one that's mobile. And so that's what they have mounted in this, 17 metric tons. And then finally, the business end of everything, once the light is captured, is to go to specially developed scientific instruments, of which there are a half dozen that you'll see in a minute here. Here is a cutaway of the way everything works. Flight deck towards the left there in the nose of the aircraft and moving back toward the right. So starting with the telescope here in the back, you can see an opening, and that's an honest to goodness opening. It's not a clear plastic or clear glass. It's actually open to space. So the aft part of the aircraft is at those altitudes about minus 40 degrees and with some buffeting in there, I'm sure. And as our project manager told us, the only people they put back there are the graduate students, which I think John Hepler can appreciate. At any rate, it's of course not true. There is a bulkhead to protect the people, and that's right here. And it's a really solid bulkhead that doesn't just allow you to have a pressurized aircraft forward of that. It also holds the telescope, as you'll see in a minute. Then there are the special customized stations of various kinds. And they have a program, and they actually have some NASA SOFIA ambassadors. I'm not one of them. There are a few of the NASA ambassadors that serve double duty. And those folks work with educators, and they have a lot of planned trips for, allowances for all-night trips for teachers and I think students sometimes. And then towards the aft, of course, is the operational part with the mission operators and the experiment operators and so on, working with the instruments that are placed into this space here, and they're interchangeable.
Hey, John?
So that's the cutaway. So what we're going to see here, December of 2009 was about a year before it went operational, and so they were still verifying the design at this point. And what you're going to see is a video that shows the first flight where they operated the door. This is about a 16 by 12 foot door, and the main external modification that you'll notice here in just a second, and I'll start it up so you can see, is that bulbous part that you see behind the wing in front of the tail section. And what that is a structure to hold the door and the movement mechanism for the door. It's cylindrical, and it serves double duty, as you'll see, in that it also provides a ramp for the airflow as it comes back past the wings, and it creates a more laminar flow across the opening. Whoop. So we'll go back to that and make it work this time. And so the chase plane is taking a look again at this first flight with the door opening. And the project manager told us that on their way over to the flight, they stopped at Target, this is true, and bought some masking tape and twine. And they have pasted those pieces of twine all around the opening to observe whether or not there was a lot of turbulence and disturbance. And it turned out that it all worked very smoothly. And that experiment helped them to understand that. So here the door is fully open. And if we stuck around for another minute, you'd get to see it close, but that's the way it works. So here is the light path from a star to that primary, back up to the secondary, which you saw, and then to not one, but two tertiary mirrors that direct different parts of the spectrum. And so, as you're probably aware, you can use a dichroic in between the secondary and the tertiary to split the colors, dichroic. And so you take the infrared and bring it in for most of your experiments, but you pick off some visible and you use that for orientation, mapping the computer star fields and so on, and also doing photometry. So here's a picture of it with the primary in place as opposed to during that open door test flight. And the secondary you see, and you can just see how serious a bracket it is that holds this whole thing. And on the left there, you see part of the ring of that bulkhead. And we'll see a schematic so you can understand that a little more in a minute. But I did want you to note that on the bracket that's hard mounted to the telescope are these two bore-sighted video cameras that give you the ability to align and match the telescope to the star field and give you really good precision for your spatial accuracy. So here is a cutaway to show you the whole assembly. That whole 37,000-pound telescope consists of the bracket and the primary and secondary and all in there, as well as the part of the telescope that comes through the bulkhead over to the left here. And the green bulkhead position there also holds something that you can kind of see in the middle, which is spherical. And so what you see is an outer sphere that is firmly attached to the bulkhead to hold it in place. And the telescope itself is attached to an inner sphere inside the outer one that's only slightly smaller, but separated by a very thin layer of very high pressure hydraulic fluid. And so it literally floats, this entire thing, as well as having gyroscopes for stabilization. And so they're able to get tremendous accuracy this way using the optical TV cameras for orientation, as well as this visible camera you see with the blue arrow there inside. So here are the half dozen instruments, and these are the only instruments that they've used so far in their little over 10 years of operation now. 5 of the 6 are infrared, 2 of them are mid-infrared, and 3 of them far infrared. And as you can see, the inner or the cabin side, the pressurized side of that spherical mount is sky blue there. And you can see the various instruments mounted on the end of that infrared light tube. And we're gonna get another view of forecast here in just a minute when you see the entire cabin. But let's take a look for just a second at the important scientific aspect of these instruments. So on this plot across the bottom, you see going from near infrared at the left through mid, through far, all the way over to millimeter, which matches up with the ALMA instrument that you see all the way at the top there, just for reference. That's in South America. But the 5 infrared instruments I'm going to talk about for a second. 2 of the things shown there with their wavelength bands, the light blue and the kind of earth pink color, are actually future capabilities that don't exist yet. But the other 5 do exist, and they've been well used. X's and forecast cover the mid-infrared region very nicely with different levels of resolving power. And the sweet spot, if you will, of the SOFIA, because no other facility, certainly not on the ground, as you'll see in a minute, and none flying in space at the moment, has the capability to look in the far infrared like SOFIA does with these 3 instruments, GREAT and Fifi and HAWK. And when I say it's the sweet spot, that's because of this. In the upper of those 2 plots at the bottom, you see the opaqueness in the far infrared of the atmosphere, even if you're at the top of a mountain like Mauna Kea. Whereas if you go up in SOFIA, in the bottom there, you see that most of that energy gets through the atmosphere transparently at about 39,000 feet. And so they're able to get really good coverage in the far infrared. And they're the only major telescope today that can do that. So here is a picture of a typical operation looking back from the educators area with some mission directors, I think, sitting probably right in the middle there, and some experiment operators at the left and in the back. And as I said, that's the forecast instrument that you can see mounted right in the center of that bearing on this side of the bulkhead. And I would love to get a flight in one of these days. All right, so let's see what Sophie has been able to accomplish. We have just a few examples here. One of the many, I think, Hubble images of something that you're all familiar with and probably have looked at this colored band quite a bit. But at any rate, long ago, we did some spectral analysis of the bands and found this to be upwelling organic material, a really massive amount of it coming up from the lower atmosphere. And that's in the visible. And then on the very first flight, just over 10 years ago in December, Sophia targeted Jupiter, and they targeted it and used the forecast instrument that I mentioned, I think, to look across multiple bands and look for where the heat was being emitted by Jupiter, and found that the most heat by far was exactly the same physical feature as the one with the upwelling organic material, just quickly demonstrating the value of having more than one part of the spectrum to learn from. And long before this, apparently about 15 years ago, another NASA aircraft observatory, I believe at Learjet, had flown missions that imaged Jupiter and Saturn and had confirmed that there was a net outflow of heat from both of those gas giants, that they put out a lot more than they took in from the sun. So a lot of that inner heat happens to come out in this same band here. So as I mentioned, by being able to plan a flight path with perfect geometry, almost literally, they were able to do an occultation experiment here with a star going behind Pluto in 2015. And you're probably familiar with how occultations give you the sum of the star and the intervening disk, in this case Pluto, that level of energy before the star is blocked, at which point you just get the energy from the disk, in this case Pluto, and then you come back up after the star moves from behind. And so in this case, what you're able to do by having really excellent geometry, if there's any atmosphere at all on the occulting object, is when you pass right through the area and are viewing the planet with the star directly behind, and they measured that it was within a few kilometers of being exactly dead center, then a lot of the star's light comes around through the atmosphere and gives you this flash. And the most interesting thing about the flash in this case was they'd done the same thing in 2011, and the height of the flash was significantly different. And so about 3 weeks before New Horizons got to Pluto in 2015, the Sophia analysis had already suggested that there was quite a bit of active atmosphere, atmosphere indicating some geological activity on Pluto that hadn't been necessarily expected. And then, as you're probably aware, all the great things that happened from New Horizon have told us a lot about geologic activity on Pluto that we hadn't expected. Another experiment that they ran, this one quite recently, I think in 2019. For reference here, I'm showing you one of those wonderful planetary nebula, in this case NGC 7027. And you see all the material that's been sort of, exploded off of this aging, dying star in the center and moving out rapidly. And they decided to look at the composition of the material of this nebula, and they found a very special molecule. And if you know your chemistry at all, and I don't know much, but I did know this, the big red blob there in the middle is 2 protons and 2 neutrons, or the nucleus of a helium. atom. And right next to it, connected there, is the one proton in the center hydrogen atom. And so while you probably didn't think that helium, being inert, could go into form this kind of a molecule, it can, and it did. And what was unique was that the cosmologists had long ago calculated, as the universe cooled initially, that the first molecule formed wasn't H2, it was helium hydride. And so here they finally confirmed in a flight of SOFIA with excellent spectrometry, the plot of helium hydride. They were able to differentiate it quite clearly from anything that might have been ambiguous like carbon monoxide here. So it was quite a finding when they came up with this. Not that these are the literal first molecules, but they are representative of what had been predicted to be a special molecule that was the earliest one formed as the universe cooled. This particular one is probably my favorite. It's a look on the right from Hubble as far as it can look into the near infrared, where it is able, as you now know, to see through a lot of the dust. But there's such a cloud or crowd of stars toward the center of the galaxy that that's the best that they've been able to do. And yet when you look through all that with SOFIA, they were able to actually image the black hole at the center of our galaxy, shown with the material orbiting around it here, the yellowish material, and every once in a while, as you see here, a star being swallowed up by the black hole. I think that's a fantastic image. All right, so that's the SOFIA platform. Now let's talk about what the space telescopes have done. The Hubble is shown at the left here, which is to represent looking today back through time all the way to the right to the Big Bang. And you've probably seen different versions of this particular chart. But the point is that we can look deeply if we take advantage of redshift, which we'll explain a little more in a second. But the first time that Hubble stared at what was called the Hubble Deep Field, in the first 10 years of its operation, or the first 5 years, actually, I think, it was able to identify an awful lot of galaxies. And when they looked at the spectrum of these galaxies, they were able to verify that they were seeing maybe as far back as 1 billion years after the birth of the universe. In other words, almost 13 billion years ago, with a redshift of 5.5, you see down there at the bottom. The record, though, awaited the Hubble Ultra Deep Field, which was what we looked at in that second video at the beginning. And the Hubble Ultra Deep Field was staring for over 1 million seconds and over 11 days total, which sounds, pretty impressive, but especially when you consider that the telescope has to be articulated and pointed and have its sun shield open and closed every hour and a half as it goes around the Earth. So accumulating 11 days of viewing was something, but they did it. And they came up with the Hubble Ultra Deep Field. And then for a number of years, different research teams tried to use the spectra to identify older and older items. And finally, the record holder, which I think is going to hold up and won't be beaten by anything else they can find. And that is known as GNZ11. GN for Goods North, the area of the sky. Z is the redshift, and 11 indicates approximately the redshift. The actual redshift turned out was 11.09, which equates to looking back in time about 97% of the way, or to about 400 million years after the birth of the universe, which I don't think anybody, when they first launched Hubble, for one thing, they really have learned an awful lot of cosmology since then. But in the 90s, I don't think anybody imagined being able to look all the way back to 400 million years after the birth of the universe. All right, so I want to dwell a little bit on redshift, because it's an interesting thing to really understand how it is that they're able to equate these things with look back time simply by looking at the spectra of galaxies. So what I've kind of honed in on here in a much larger slide that NASA gave me is this area of energy that's emitted by a typical nearby galaxy. In other words, all those wavelengths from ultraviolet to visible to near infrared and beyond are present in a typical galaxy. And yet there's a very special feature that they take advantage of, because when the universe expands, the photons flying through it have their wavelengths stretched. You can picture that like that picture back toward the beginning. And so you go in the direction of red. If you're at ultraviolet, you go in the direction of visible to the right. If you're in the visible and you're at red, you go beyond red to near infrared, and so on, to mid infrared, and so on. And so that's the stretching that is equivalent to the expansion of the universe. And so what we have as a special feature is this end of that spectrum, which exists for all of them. It's a fact due to the structure and the emission and absorption of hydrogen. You have what are called hydrogen lines, and one of them is the Lyman line, and there's this hydrogen break. And what it is, it's a very steep drop off in the energy in the ultraviolet at about 0.1. And the reason that it's so important, it is, as the galaxy is further and further away, all of that energy will be shifted to the right, as you'll see in a second, indicating a higher and higher redshift number and indicating the amount of time that the universe has been expanding to cause that redshift. So let's take a look at what happens as the universe expands. And the Lyman line is always visible as a sharp drop off there that makes it easy to spot. And it also eliminates the energy to the left of it, so that the images that you saw across the bottom there, which are 9 in number, those equate to the 9 different filters. And those images literally were, I'm going to see if we can do this again here. They disappear as the filter no longer finds any energy coming through its part of the spectrum, until only one filter was left out here at about 1.6 microns. And that's the one that identified that GNZ11 galaxy. And I can finally make the point then that this is the limit of what Hubble can do. It can't look any farther, and therefore it can't look any farther back, because any further back for that Lyman break would take it out of the field of its spectral capabilities. Enter the other telescopes. So here, just for reference to what you looked at before, I've shown where Hubble looked in terms of wavelengths. It's off to the left, literally, in terms of all the capability that SOFIA has. It only reaches a ways into the near infrared there, and yet even with that, we were able to see back a long ways. You heard last month about Spitzer, and here's where Spitzer sits. Wonderful spectral coverage across the mid-infrared and well out into the far infrared, except that, as he told you, I think it was within the first year, after about a year, they no longer had the really cold cooling of their far infrared focal plane, and therefore they were only able to use the mid-infrared part of Spitzer. And Spitzer was great for that while it was flying, but what it didn't have that Hubble has, that SOFIA has, and that the James Webb will have is spatial resolution. And so here's what the Webb is designed to cover, overlapping a bit down into the red region of the visible, but well out across the mid-infrared. And so it's going to be a true infrared telescope with very high spatial resolution. And so there it is. And we're calculating that it's going to reach quite a bit beyond that redshift of 11, and perhaps well beyond 11, which would mean that it's going to be able to see back 100 or 200 million years more towards the formation of at least the first galaxies, if not the first stars. So it's a pretty exciting time for astronomers and all of us, I'd have to say. So here is, just for kind of reference, a faithful spatial or physical comparison between Hubble and the James Webb in terms of size. In terms of the primary mirror size, 2.4 to 6.5, which means that the Webb is collecting almost 6 times as much light as the Hubble did, and Spitzer was less than a meter. And so James Webb is going to be collecting whatever that works out to be, 20 times, 40 times more light than the Spitzer did. And the other major difference, of course, is the wavelengths. Now, in order to do that, you have to have cooling. Hubble operated at room temperature by design, which allows you to look a little bit into the infrared, but not very far with much sensitivity. But they were clearly successful into the near infrared. The James Webb, like the Spitzer, is planned to be a very cold telescope. The entire telescope is going to sit always with that multi-layer sun shield underneath all the working elements, always between the working elements and the sun. And so it'll be able to cool down and stay cool. And it will also have the ability to get even colder than 40 for one of the instruments, as you'll see. But that cold temperature is critical to being able to look through the near infrared and into the mid infrared. The Hubble, I want to note, you may have read this in the last month, literally, I think about a month ago, or maybe a month and a week, there was a report that Hubble was experiencing some problems. They had some software problems on board. I'm sure they figured it out by now, but what it caused was a complete automatic shutdown of the entire spacecraft in order to, it's just something, it's called a safe mode. And then gradually they brought it back up online. They fixed whatever it was and now are back doing full science operations. So in 2 weeks, I think, or a week and a half, the 24th, I think, is the anniversary. So 31st anniversary, remarkable, and may have many years more to come. We hope so. All right, so here's for, I think, useful physical reference, a person or two standing near the James Webb, just to get a feeling for just how giant this telescope is. And even as you see it there with its 18 segments, you have to wonder how you get this in a spaceship. Well, you fold up the wings. 6 of the 18 segments fold back. The multi-layer sun shield folds up and then rolls up into dispensing canisters, and it all tucks inside the fairing. The mirror itself is quite interesting, the primary. I think it's kind of remarkable that each of these 18 segments, which is about 50 inches in diameter, only weighs about 80 pounds because it's made of beryllium, specially chosen because it doesn't have any thermal expansion or contraction in the range where it's going to operate, and also coated with the best possible reflective coating. And then a special feature is to put on the back of each of the 18 segments identical sets of 7 actuators, where 6 of them allow you to tip and tilt that section so that you can establish first the 18 segments in a macro perfect parabola, and then you can actually use one of those actuators to slightly change the shape of each of the segments in order to get just the right mirror figure. So as you can imagine, between the time that it's going to take to cool down and the time that it's going to take to form the exact perfect shape, it's going to be a while once they get on orbit before they can actually have first light on the telescope. I would also note that each of those, I mean, it's one thing to say that beryllium doesn't expand or contract between 0 and 100, but we're building these at, our temperature, 300 Kelvin. And so they have had to take, they have basically built a misshapen segment and then put it into the cool down chamber that they have for months in order to verify that when it cooled down to, I think they were able to get it down below 10 degrees Kelvin, that it actually did attain the shape. That was critical. Took some planning and fabrication. All right, on to actually getting this launched. And the launch is, as I said, planned for Halloween on a pretty special booster, which you may or may not recognize. It doesn't fly from any of the NASA sites. It's a European one, and you could have known that by knowing your rockets, or you could know it by reading the tower. The launch tower indicates that it's European Space Agency. It's the Ariane 5, their largest booster, and it launches from the east coast of South America. And it does that, of course, in order to get the maximum payload by being almost on the equator and launching almost directly to the east. And that's why NASA chose this big booster. It's been an extremely successful booster for the Europeans. And this is either the last or the next to the last one of them before they go to their next generation. So come Halloween, we'll all hope that the launch is successful, and then will be the beginning of a very high anxiety, very long time, because it's going to take a month to go through the configuration on the way, to fold the wings out and establish different things in place and get to the second Lagrange point. You may remember in the two-body system, there are 5 stable points, and one of them, in the case of the Sun-Earth two-body system, is beyond the Earth in line with the Sun. It's called L2. And if you get straight out there, you'll both be in a stable place where the gravity will keep you there without much station keeping, but you'll also be in the Earth's shadow, which, believe it or not, is not what you want to be, because the Earth's shadow is pretty small. And if you drift in and out of it, it would be a terrible problem for heating and cooling on the entire structure. So when it gets out there, it goes into a halo orbit, which it sort of swoops into this orbit that always has, as you can see, the sun shields pointing back towards the sun, and it's a circular orbit around the L2 point. Again, very stable orbit. And that's where it'll be, hopefully, for not just years, but maybe decades, like Hubble has been. And so beyond the month that it takes to fly out there, to almost 1 million miles beyond Earth to that point, it's going to take another month or two to have passive cool down to the 40 degree Kelvin, and then all that arrangement of the segments into the perfect mirror. And it may be about 6 months after this, I'm going to guess, when they can finally declare full operational capability, which would be, given that it's October 31st, just about now, next year. So it's a pretty exciting time to be watching for. All right, so here are the 4 instruments that were designed some years back, because the research teams had to put in proposals, as you'll see, a long time ago, in order to come up with the selection of the best science they could do, which changed through the 20 years that this thing's been being developed. And at some point they had to freeze the design. The Europeans built the 2 on the right, the Americans the upper left, and the Canadians the lower left. And we don't have time to talk about these special instruments, but I will note that one of the 4, the one that works in the middle infrared, actually has active cryocooling, just as Spitzer did, to take it down to 6 degrees Kelvin in order to have the right sensitivity at the wavelengths of mid-infrared versus the near-infrared. And last but not least, I like to talk about this near spec, which has this wonderful plate, if you will, in the optical terrain, where there are 62,000 of these little rectangular doors. You can see the small size of them there, that can be magnetically opened and closed after being addressed on command, and they can take up to 100 spectra of stars at the same time by using this addressable array. Kind of a fantastic design. An engineer would appreciate it. The goals for the James Webb, you won't be surprised at, given how far back in time it's going to be able to look. We're hoping to get back almost to first light. We're expecting to be able to see not just what Hubble did, which was a lot already in terms of many different kinds of galaxies at different ages, but lots more, all the way back to the very first galaxies, and basically build a time slice of different kinds of galaxies to understand the evolution and the assembly of them. And then the spatial resolution will allow them to not only get much better views of these protoplanetary systems of collapsing gas star disks, spinning disks, becoming hopefully stars. In the case of each of these taken by Hubble, the star has lit up. But in the case of the infrared capability of the Webb, they'll be able to see the dark disk, and with the resolution, be able to see cooler, and it won't even have to wait for the star. And in some cases, we'll see well after the star's lit up, see these disks forming into lanes as planets form, and hopefully actually see directly some of these planets and be able to identify some of those life-related molecules in the infrared part of the spectrum. So 4 big goals. And this might look like an accident that I showed you a picture of my front yard by mistake, but it's actually a NASA scientist slide because they wanted everybody to understand how exciting they are, how excited they are at this point. And it's not just that they're impatient, it's that when this was actually approved as a platform was the turn of the century. And so the initial launch date was 14 years ago. And that wasn't just throwing a dart at a calendar. They actually were hard at work for those years as one delay after another set in. And so you can see here again by the date of when NASA set up the initial science team after approval for the James Webb with the European and Canadian space agencies as partners. And this science working group solicited research ideas. And so there have been, if you can picture it, 2 decades of teams of scientists around the world in probably hundreds of institutes competing for the investigations and the research projects. They have been defined, and you've got literally thousands of scientists waiting for the data to arrive starting about a year from now. It's pretty exciting. So the first cycle, the first programs known as cycle 1 will feature guaranteed time for some of these teams, but it will also feature a dozen, I think, early release science projects that were selected by the director's team as the director's discretionary early release science programs, and they will get priority for use of the telescope in the first 5 months. So if you went out to any one of these Space Telescope Science Institute's web pages, which I show you in the box here, and just put in STSCI and GTO for guaranteed time observation, or ERS for early release science, you can read all the details about who's got which project to do what. And I just thought I'd highlight a few of the over 100 projects that there are, which align, as you'll see, very nicely with those major objectives for the James Webb. All right, so that's it, and hopefully there will be some questions.
Thank you, John. Thanks.
Hey, John, this is Chris. I have a question on the Sophia. How do they keep the seal between that spherical bearing and the inner cabin sealed so that they don't lose the pressure from the cabin?
Can you hear us, John?
I can. Let's see. He didn't tell us, and I'd never thought about it. It's a good question. And rather than just say your guess is as good as mine, which is probably the best thing to say, the answer is I don't know, because I haven't asked, and I haven't seen that level of design. But I mean, you're talking about holding pressure in the pressurized part. Yes.
Yeah. I was just curious if they could actually change an instrument out while the plane is in flight.
Oh, I'm sorry. Yeah,
you know what I'm saying. If you take it out of there, would you lose cabin pressure, or does it have to be installed before they take off? Or
yeah, no, I do. I should have said that. I somehow missed that point. Each of the 6 takes about a day to both install and also to take out. They only fly one at a time. And so when they go down to the south, for example, for a month or 2, they take a few of the instruments down there with them, but they're all about 1,000 pounds, give or take 100 or so. So they're not small, and they do take, the better part of a day to install. So they don't do that while they're in one of their 8-hour flights.
Okay, well that kind of answers my question. And once it's bolted on, I'm sure it seals it up to the flange and doesn't leak.
Mm-hmm.
Yeah.
John, my question is actually one more of your personal opinion than it is anything technical. Do you think, given you've seen plenty of projects come and go, you've seen them succeed and fail, we saw what happened with the Hubble and its initial problems with its mirror. Do you think that coming up this October, we're going to be having another one of those watershed moments that'll either, make or break the NASA science program at this point with the success or the failure or glitches with the James Webb Telescope? And this is, I'm asking Sheila your personal opinion since you've been around long enough to see a few of these happen.
I've given this talk. It's a great question, and not to make it smaller, but I get this question a lot. And as a matter of fact, I'll tell you that the first time the James Webb, I think it was the principal scientist or the project manager talked to us maybe 5 years ago. I asked the question when he was done about servicing capability at the L2 point. And the answer was quick and clear, and it was no. And fortunately, he thought a little more about it then and said, yeah, we'd like to, but no, there's been nothing designed in to allow for that. The next time or 2, it wasn't brought up. About a year ago when they talked to us again, this time it was noted that they had put some kind of, now I'm reaching back into my memory, whether it was that they were considering what kind of a space tug could be put into near Earth orbit and deployed out there, or whether they had, I think they may have, I don't think that was it. I think it was they'd actually put some features onto the spacecraft that would allow for something to rendezvous with it, I guess. He didn't say that, but they'd finally not just thought about it, which I'm sure everybody did every day. I mean, you imagine there are plenty of people that are in their 40s now that have spent their whole career on this. And a lot of people want to know what's going to happen, as you said, Dave, if everything doesn't go right, as it's going to have to for not just days and weeks, but months. And it's a big risk, and there is no servicing capability at this point, which is what makes it uniquely different from Hubble in 1990 when it didn't focus. In that case, it took them 3 years to figure out how and to design the eyeglasses for it, but they were able always by design to go up with the space shuttle and do something about it. In this case, they have no plans to visit it. So there are a lot of people that have kind of bet their career, I'm afraid, on this. And my opinion is I'm going to pray and hope just like the rest of them do. And a big project almost never has everything go right. And there are a whole bunch of things about this. They've tried to test everything possible, but who knows? I mean, you can imagine that putting all of that sensitive stuff now inside of a big booster and vibrating it up into space is no small, thing to hope that nothing shakes or, misaligns in any way. So there are a lot of things that can go wrong. I guess I should just say that. And as far as I know, they don't actually have any capability at this point to go visit it and fix it if it does.
I was just thinking more in terms of, I know that there are certain congressmen and senators who have been absolutely key in maintaining and extending funding to make this project happen. And I forget the percentage over budget that this thing is going to wind up being because of the delays. And I'm not thinking about this project, but I'm looking ahead saying, okay, if this thing doesn't go right, what impact do you think this will have for NASA on the next project where astronomers want an instrument that may be more complex, that may be a more daring and more complex mission or spacecraft or telescope? What will that do to NASA if this does not succeed the way we want it to?
Yeah, I can tell you that one of them that's very relevant that I believe, fortunately, the program people fought hard enough to keep Trump from killing it, which he tried every budget year, was the W-FIRST, the Wide Field Infrared Space Telescope, which is going to be the next big one, which is also going to be deployed at L2. And that, now the earliest launch date is going to be maybe 26, something like that. It's a simpler telescope. It only has 2 instruments. It has not just a proven, what did I say, 2 telescopes? I meant 2 instruments. If I said telescopes, it's not just a proven telescope, it's one of our spy satellites. Okay, it's that one. And so it's got a higher probability in some ways. Nonetheless, it's also going out there where it can't be reached. And it's going out there only about 5 years later if they actually hit all the marks. But like I said, over the last 3 budget cycles, it was tried to be killed, but NASA managed to keep their money in there. So again, there are people, like you said, politicians that have probably put down their markers on that one as well. And it's well along now, at least. If it were sitting here waiting for James Webb to either work or not a year from now, then it would have delayed the whole program 4 years. And as you were implying, I think it's probably true. If the Webb doesn't work, people would think hard about even starting it at that point. It would have an impact. There's no question about it. I believe that the impact should be especially felt in terms of rescue capability and servicing capability, and that should be more of a primary consideration in any program this expensive in the future. We got plenty of things in near Earth orbit, which I have to say, like the Spitzer and other things that didn't have any ability to be serviced either. So it's not necessarily just being nearby, it's being part of the planning and part of the engineering, so that you have at least worked through the scenarios of where will you hook up, what can you do, can you take this in and out, what's modular, what isn't, those sorts of things. So Hopefully they'll do more of that than they have with the web.
Thank you, John.
Sure.
Hey, John, this is Bruce.
Yeah.
Sort of a follow-up question, not dwelling on the possibility of failure, but given that this won't be serviceable, and the same with the W first, do both scopes have even greater system redundancies than a normal project would have? You know, simply to build in more things so that if something goes wrong, you could maybe compensate.
Let's see. You heard my talk on Cassini,
Right.
and my talk on, I think it was one of my rocket science lectures, the
Right.
one about spacecraft systems.
Right.
I believe, but not because we've ever actually had a briefing on the actual spacecraft systems themselves. I believe that they've probably designed in all the redundancy that they typically do for all of our, you know, high value spacecraft. I have to believe that. But the science parts of it, there are just plenty of aspects of that I'm sure they won't have redundancy for.
Right. Right.
Not the least of which is, you know, if one of the segments has an actuator break or something, who knows? Who knows? So I guess my answer to your question is I don't actually know, Bruce, beyond assuming that as good engineers, they've really designed in redundancy.
Okay. Thanks, John.
John, it's Don Miller. Nice talk. Question on orbital mechanics. So how do you orbit a massless point like the L2?
There's a really good YouTube that shows literally as you approach the orbital, as you approach the distance, it's not like you go straight out to L2 and then decelerate and then hang a right and,
Yeah,
and
exactly.
move a little bit away from L2 and then hang another right and accelerate into a circle, okay? It's a sweeping maneuver. And part of the reason why it's a sweeping maneuver is because of the fact that they will have opened everything up at that point after the first couple weeks. And by the time they get out there in the last 10 days or so, they will actually move into not a straight direction, but they will actually sweep around and curve in on, sort of rotate in on the halo orbit, which is, and as you can picture, a halo orbit that's going around a moving point on the circumference looks like a coil. And so they sort of swoop into it in the last few days. And they did it partly purposely to not have any heavy mechanical loading because everything's going to be opened up and they don't want to get anything that experiences shocks or vibrations.
Makes sense. But normally you think of an orbit as around a massive body, not around a no mass point like L2. So it must be the Coriolis force that's actually causing it.
No, it's all about gravity and mass. And it's about the gravity of mass of two bodies. And it's no, it's not simple. It is an elegant, and I forget with which mathematician, well, it was Lagrange that eventually worked it out perfectly, but somebody like Huygens or somebody else that I can't remember at the moment came up with the idea first. You can solve for the 5 stable points in a two-body system.
Right.
One of them is between the two bodies. One of them is beyond each of the two bodies. So there are 3 lined up, and then there's one that's 60 degrees ahead of and 160 degrees behind the orbit of the smaller of the two bodies. As a matter of fact, one of our one satellite we were looking at the other day, I'm forgetting which one it was, is actually in orbit. Spitzer. Spitzer was at he didn't use the term, but I looked it up after I listened to his talk, and they were at the L4 or L5, which is one of the two that are in the Earth orbit, trailing or leading. with one or the other. And as he pointed out, eventually that orbit would decay and be pulled toward the body, but be turned around before it got there in what he called a horseshoe. And
Okay.
go back and forth on that horseshoe literally forever.
Thank you.
I mean, that's orbital mechanics for you. The Lagrange points, as you would imagine, because everything in orbital mechanics is subject to perturbations. And one of the main perturbations when you're going around a body like Earth is the fact that the body isn't homogeneous, it's lumpy. And so the Earth is oblate, it's fat at the equators, it's also pear-shaped, not to where anybody would see it, but it is. And so you have to solve for that in the orbit, and it causes what allows you to have sun synchronous orbits, so that the orbit going around the Earth in a polar orbit, if it just did that around a perfect sphere and you went around the sun, the angle would change, the sun angle would change all the time, of course. But if you put it at just the right sun synchronous orbit, because of the perturbation of the shape of the Earth, it rotates 1 degree a day roughly, so that it always maintains a common shadow as it goes around.
Cool.
And the L1 through 5 Lagrange points are not literally points because of the perturbations. They're a little volume in space where the gravitational attraction of the two bodies is felt the same and allows them to stably stay there without drifting much at all. So
I think
John
there's a question
Hepler
on-
has either struck a pose here for us, or I like the picture he's put up.
John, there's a question in the chat.
Yeah.
From Shiv. Why aren't there pictures of galaxies in gamma rays? Are there gamma ray telescopes?
Yes. NASA started off with what they call the Great Observatories program in the 80s. And the first one that flew, we actually bid on over in King of Prussia. It was known as GRO, the Gamma Ray Observatory. It was then known as Compton, named after, I think, Arthur Compton, the physicist. And it flew, I believe, in the 90s. And then there was another gamma ray observatory after that that I've forgotten the name of. So we've had multiple big gamma ray observatories.
So the Spitzer just floating out there now? It's no longer active. It's just floating around.
Well, that's what I was saying about the orbit. Somebody asked him, I think, that question last month. It's not going to go anywhere. Unlike, you sometimes need to, in order to keep the interplanetary space secure and free from loose satellites that can crash unintendedly into places you wanted to keep pristine. You have to, intentionally drop them into the atmosphere of Jupiter or Saturn, for instance. In this case, orbital mechanics keeps Spitzer in that orbit, not right where it is. It will be attracted towards Earth, but before it reaches Earth, it will be repelled by, sort of like when you have a slingshot for some of the planetary orbits, and go back around the other way and just, as he said, do that eternally. Gravity will keep it in orbit out there, dead.
So if there's enough room inside the thing, do you think that SpaceX could use it for space tourism and convert it into condominiums?
Always the
these-
entrepreneur.
Or
These
put another,
days, I'm absolutely sure that everybody is thinking about things like that all the time. Out of the box thinking used to be quite a bit more mundane than it seems to be in the space industry.
Another question in the chat from Bernie. Will Webb be able to identify industrial or organic type gases in the atmosphere of exoplanets? I think it's referring to the kind of work that Sarah Seeger is doing.
I'm not sure I understand the question completely, except all I know is that they certainly have a lot of spectroscopic capability on board. As I said, they can image stars easily, and get individual stellar spectra. There are multiple techniques for looking at exoplanets and looking at the composition of the atmosphere of exoplanets, for example. WFIRST, and I'm trying to remember, is there another one? At any rate, WFIRST, and I think there's another telescope in planning, uses one of these systems, somebody help me out, that blocks out the star in the center. What's the name of that? You know what I'm talking about? It's like a paddle.
I can't think of it, yeah.
Yeah.
You're talking about
At
a
any rate,
compass?
WFIRST is going to have one of those. I don't know why the name slipped my mind, so that they will be able to directly look at stars in the Milky Way, certainly not outside of our galaxy, and block out the light from the center star and hopefully directly image the exoplanets. There are other ways to look at the spectra of exoplanets as they pass just around behind a star and come out from behind it and look through the sun's atmosphere, or see if I can get this right, have an object behind them, have its light come through the planet's atmosphere and be able to actually image and measure and then spectrally separate the elements of the atmosphere. I'm saying this very badly, but that's already done somewhat with the exoplanets. I haven't read anything about Spitzer that says that that is an area that they are specifically doing, but I haven't begun to do much to look at that 100+ research projects, and I would almost bet that there are some in there that are planning to do that.
A question, will the James Webb be used at all for any sort of planetary or solar system research?
I'm sure it will. Yeah, it won't be a priority, but it's uniquely suited in the near to mid infrared, and with that resolution to do some things. And so I imagine at some point they'll do some of that. They for sure are going to be looking at stars that have been hard to see within our own galaxy, out in the bulge, I think, and above the plane, as distant as they can, which Hubble hasn't been able to do very well.
Would the James Webb be able to see through Titan's atmosphere?
I don't know. I don't know. I'd just be guessing. We haven't had on Cassini an instrument that's been cooled like that, that's had that sensitivity in that part of the spectrum. So I don't know how much of the atmosphere it would be able to see through. Of course, a lot of the problem with Titan is simply the thickness of the atmosphere, not just the temperature of it.
Thank you.
John, I think you showed how infrared is blocked even at a Hawaiian telescope, right? Because there's a question about infrared telescope.
Yeah, that was Mauna Kea that I showed. It's in the far infrared from the 30 to 300 is like nothing. You just can't see anything no matter how high you get on the Earth. But if you go up to 40,000 feet, you get about 80% of the energy coming through.
Oh, okay. I think that's everything in the chat. We got all the questions answered.
John, thank you so much. That was a fantastic talk. And once again, you've really given us a great presentation for our members and for the other societies as well. Thank you so much.
Yes.
You know,
thanks,
I
John.
really,
Thank
I
you.
really learned a lot from the Spitzer talk too, and it did help actually inform mine today some. So I appreciate the opportunity. Thanks a lot, guys.
Great.
Thank you.
John.
So-
Thanks.
Thank you.